So in this video, we're going to cover a couple of topics in the second part of, Unit 1. We're going to talk about light and the electromagnetic spectrum. We'll talk about the photoelectric effect, photoelectron spectroscopy, and then finally a review of Beer-Lambert law. First of all, let's just review spectroscopy and the electromagnetic spectrum. Spectroscopy is simply the study of how matter and light interact, and there's many different types of spectroscopy. You're already familiar with spectrophotometry, which is one of them, and in spectrophotometry, we're looking at how light is absorbed in a solution, and we're typically dealing with visible light, sometimes ultraviolet light, but that's only one branch of spectroscopy. And at the end of this video, we'll be reviewing Beer-Lambert law, which is really about spectrophotometry. So what are the other types of spectroscopy that we're going to learn about? Well, one of them is spectrophotometry, also known as colorimetry. Another is photoelectron spectroscopy, which is an important focus of this unit in the AP Chem curriculum. And then finally, we're going to touch on infrared and microwave spectroscopy, which are really sort of an afterthought in the curriculum, but important to mention. In all of these applications, we need to understand what light is. And we've talked a little bit about the wave model of light in this equation, C equals lambda nu, where C is the speed of light, lambda is the wavelength, and nu is the frequency. We're going to talk a little bit later about this particle model of light equation, which is going to include Planck's constant and the energy of the photon that's released in just a moment. But let's just review the wave nature of light. We know what a wavelength is. We know the difference between high frequency waves and low frequency waves. And we understand that red light, for instance, is a lower energy wave than blue light. And this equation is an important one to be familiar with. There are some simple calculations you might be asked to do. Just pay attention to units and know that this term, the frequency, is in units of per second or hertz. And that makes sense. If we take meters and multiply by per seconds, we're going to get meters per second. On the reference sheets, the purple papers as I call them, the equation that's printed here is given, so is this constant. And you might be asked to do a calculation like this. Find the frequency of green light that has a wavelength of 545 nanometers. Now a nanometer is 10 to the negative ninth meters, so it's a really small fraction of a meter. And once we do that unit conversion, this is just a simple algebra problem of plugging those numbers in, rearranging to solve for frequency, and of course our answer there is given in hertz. That are the units for frequency. So remember that this Greek letter nu, it looks like a V, is not velocity. The speed of light is the letter C. This is frequency in hertz. So that is one aspect of the wave nature of light that we should be familiar with. We can calculate frequency and wavelength in terms of the speed of light. And we could think about the electromagnetic spectrum as a continuous spectrum, whereas wavelengths get shorter and shorter, shorter and shorter, then the energy gets higher and higher. However, there is another way of thinking about light which is important, and that's because light that is emitted by atoms is actually quantized, and the spectrum is not continuous in this context. And this is what Max Planck hypothesized when he noted that the light emitted from a heated object like a stove element or a light bulb filament actually kind of goes up in steps, or is emitted in sort of discrete quanta as the temperature increases. So we might think of as you turn the dimmer switch up on your light bulb, or as you turn the temperature up on your oven, that the energy of that heated filament is just going to increase in a linear fashion. But Planck suggested that it actually increases in a stepwise fashion. And this is really what's at the heart of the concept of quantized energy. This, not all energy is quantized, but the energy that's released from atoms when they're excited is quantized. And there's a reason for that that we need to understand. And that's because it has to do with the energy transitions that electrons are going through when they release those quanta of energy. This equation is printed on our purple paper right next to the other equation underneath light and electronic or atomic structure, and it relates the energy that is released by an electron to the color of light or the frequency of the light that's released by Planck's constant. And essentially what this equation is telling us is that it is always going to be a multiple of Planck's constant. The energy that's released can only have certain allowable values. That's a very, very small number, kind of showing us that the scale at which this quantization exists is a really, really small scale, almost imperceptible. But it's true that the energy of light that's emitted by electrons can only be a multiple of this number. And that's really the key idea. So here are the two equations that we want to be familiar with. In order to understand spectroscopy, we need to be able to work with these two equations. You can see that they can be written together as E equals hc over lambda, but they're given to us on our purple papers as just this wave equation and the Planck equation. So be prepared to do calculations with these, although they only come up occasionally. They will really just be a matter of plugging some numbers into an equation and doing some calculations. There are a few other concepts, though, that we want to discuss which are related to these equations. The concepts that are related to those equations have to do with the photoelectric effect and photoelectron spectroscopy. So let's talk about those next. First of all, I want to go through a few slides here which describe the photoelectric effect and sort of a historical context. What's being depicted here is a simple circuit where a battery is allowing electrons to flow through a wire, but you can see there's a break in the wire here, and electrons are allowed to jump across the plate, and if they complete that jump, then the lamp will glow. In other words, we will see this lamp lighting up when electrons are actually able to jump across this gap. With the gap being large enough, electrons won't be able to make the jump. So if we begin with this, the way it's shown, before we shine green light on here, this lamp would not light up. But the science world knew that certain clean metal surfaces would shed electrons when a certain frequency of light was shined on them. So this picture is trying to show that if I shone a green light onto this metal plate, it would cause electrons to be ejected from this metal plate and make it all the way to the collector, and the result is the lamp would turn on. However, if I use red light instead, the lamp does not turn on. And what was interesting is that it didn't matter how bright that red light was. What mattered was the color of the light. In other words, the frequency of the light. So we have to distinguish between light intensity, like a bright red light or a dim red light, and light energy, like a red light or a green light. Even if I shone a really bright red light on the metal plate, that's red light is not enough energy to dislodge electrons from this plate and jump to this one. The second fact that the science world knew was that if I switched to green light again, enough energy to get the electrons jumping, then the brighter I shone that green light, the more electrons would jump. So there's a certain threshold frequency. Red won't do it, but green will. And the brightness or intensity of the green light actually tells us how many electrons are going to be ejected. So the brighter this green light was, the more this lamp turns on. Increasing the intensity of that light, in other words, the brightness, not the frequency. The frequency is just the fact that it's green light, but increasing its intensity causes the electrons to come out at a higher rate. If we increase the frequency of the light to purple, that's a very, very high frequency of light, high energy of light. Now we get the electrons to come out even faster. but they're all going to come out with the same speed. So this really gave the science world a lot to chew on. There are a few questions which we can look at now which talk about the photoelectric effect. So we're going to jump straight to those and take a look at questions 15 and 16. So we have a little bit of background knowledge about the photoelectric effect. Let's talk about its application in photoelectron spectroscopy, which is an important focus of the curriculum. The analogy that we're going to make is that of a soccer player in a ditch. And if you imagine this soccer player in the ditch, this ball is down here at the surface of the ditch, and we're going to discuss how much energy you'd need to kick that ball in order to get it up out of the ditch. It would need, in this case, 45 joules of energy. So if you kick the ball with 45 joules of energy, it would get exactly that high. It would be able to roll out of the ditch with not a lot of extra velocity. 45 joules would be just enough to clear the ditch. If you kicked it with 46 joules, then it would come out of the ditch and have a little extra rolling energy as well. How does this possibly relate to photoelectron spectroscopy? Well, let's first consider a ditch that has different levels. One of them is way down at the bottom, where our first soccer player was. The second one is a little higher, a little farther away from the Earth's center. And for that reason, this soccer player wouldn't need quite as much energy. Well, you can maybe see the analogy coming. Here, we can look at a lithium atom and consider the 2 electrons in the first shell to be akin to 2 soccer balls at the lowest part of the ditch. Those are at such a low energy state that it's going to require a large amount of energy to eject them. Similarly, a lithium atom's core electrons are at such a low energy state that it would require a really high ionization energy to eject them. Meanwhile, this soccer player is a little higher up. In other words, this electron in the second shell is a little farther away from the nucleus, and it's going to require less energy to eject that electron. It'll require less energy for this ball to be ejected from the ditch. So let's talk about photoelectron spectroscopy. Photoelectron spectroscopy uses X-rays to eject electrons from an atom, just like the soccer player uses a kick to get the soccer ball out of the ditch. So it's really a type of spectroscopy. How does light and matter interact? But we're using X-rays. Remember, spectrophotometry used visible light. X-ray spectroscopy is photoelectron spectroscopy and uses X-rays in order to do this. Electrons are only going to be ejected when you use a high enough frequency of radiation, like X-rays. Just like the soccer ball will only be ejected when a strong enough kick is used. And the closer the electrons are to the nucleus, the higher energy of X-ray you're going to need. The nice thing about photoelectron spectroscopy is we can also see how many electrons are ejected at each frequency, which is analogous to finding out how many soccer balls are in each level of the ditch. And that's how we find out how many electrons reside at particular energy levels, or even at particular energy sublevels. So, let's take a look at this slide, which summarizes some of those key ideas. First, let's talk about the valence electrons, which are relatively easy to remove. You can see we're talking about this soccer ball pretty high up, pretty far away from the core of the Earth or the center of the Earth, just like we're talking about this electron, which is pretty high up. In other words, it's pretty far away from the nucleus. Those are at such a high energy state that they only need a low amount of radiation to remove. So high energy level electrons have a low ionization energy. Now let's talk about the core electrons. These are the soccer balls down on the very bottom, the electrons very close to the nucleus. They are at such a low energy state that they need a lot of radiation energy to remove, high frequency X-rays. So low energy electrons require high ionization energies. Those that are close to the nucleus, core electrons, are going to have higher ionization energies. And photoelectron spectroscopy really just is the study of these amounts of energy were needed to eject electrons, so it's related to ionization energy. We can understand atomic structure, electron configurations, periodic trends like ionization energy, and that's why this is an important technique to just be familiar with. What are we actually measuring? We're measuring the amount of energy that's released when an electron is ejected. So we actually choose the energy that we apply. In other words, we're going to decide which type of X-ray we want to use, like how strong of a kick we want to give, and that may or may not be sufficient to remove soccer balls from the ditch or remove electrons from the atom. But if it's just enough, then the electron will come out with not a lot of leftover energy. If it's way too much, then the electrons will come out with a great deal of energy, sort of like when we used purple light in the photoelectric effect example before, the electrons came streaming out with high velocity. So photoelectron spectroscopy is actually measuring how fast the electrons are moving when they leave the atom, and also the number of electrons that are coming. So we choose a certain amount of photon energy, an X-ray, for instance, that has so many megajoules per mole of electrons, and we hit atom A with that, and you'll recognize this is first ionization energy, which is being described here. A neutral atom forms a cation and an electron is released. But we can measure the amount of energy that electron comes out of the ditch with, so to speak. Now here, if we supplied 25 megajoules of energy and it comes out with 13, that must mean that only 12 megajoules of energy were needed to clear the ditch because it had this much leftover energy at the end. So there's a lot of conceptual background there, but the application of all of those concepts is really the most important ideas that you'll be asked about. And what I'd like to do in order to practice that application is to look at a whole bunch of examples of photoelectron spectroscopy graphs and then explain the axes and how to interpret them. Here's a photoelectron spectrum for hydrogen. Notice the y-axis is the number of electrons, and the x-axis is the amount of energy that's needed to eject them. This is the potential energy of the electrons in their first shell. Here is a photoelectron spectrum for helium. Notice that the amount of energy that's required is similar, but twice as many electrons are ejected for helium. Makes sense? Helium has electron configuration 1s2. So 1s1, 1s2. What's lithium going to look like? Aha, 1s2, 2s1. We can see here there's two different ionization energies. One of them is for the core electrons, and the other is for the valence electrons. The x-axis here is inverted. The high numbers are at the origin, and the low numbers are out to the right. Why would that be? Well, this allows us to think of the origin as being the nucleus of the atom, and as you get farther along the x-axis, we're getting to valence electrons. And so we can kind of read the graph left to right now the way we'd think about the electron configuration. 1s2, 2s1. You might guess what beryllium is going to look like. 1s2, 2s2. There's two electrons that are core electrons and require a really high ionization energy, but there are also two that have a much lower ionization energy. And as we go along the periodic table, going along a period, you can see the pattern continues. 1s2, 2s2, p1. This is a boron atom. Here's carbon, 1s2, 2s2, 2p2. In other words, the first electrons to be ejected from a carbon atom when we hit it with X-rays are the 2p2 electrons. They only require 1.09 megajoules of energy per mole. Then there is another threshold of energy. If we start hitting it with even higher energy of X-rays, then we start seeing electrons coming out at this level. These are the two s2 electrons. Then finally, it's not until we, oh my gosh, that's a lot more energy that's needed for these, not until we get up to 28.6 megajoules per mole that we start kicking out those 1s2 electrons. Of course, both of the 1s2 electrons have the same ionization energy because they both occupy exactly the same subshell. Nitrogen, 1s2, 2s2, 2p3. Oxygen, 1s2, 2s2, 2p4. Fluorine, 1s2, 2s2, 2p5. And hopefully it makes sense in neon why this peak is 3 times greater than either of these, because there are 3 times as many electrons in the p subshell as there are in an s subshell. Sodium, you can see the 4s1 peak revealed here. And here the 3s1, and here the 3s2. And for aluminum, you can see the 3p1, and for silicon, the 3p2. For phosphorus, 3p3, and for sulfur, 3p4. Chlorine can be read on this photoelectron spectrum as 1s2, 2s2, 2p6, 3s2, 3p1, 2, 3, 4, 5. So hopefully the photoelectron spectra make a little bit more sense now that we see the pattern of electron configurations being filled. Here in potassium, you see the 4s1 peak being the farthest to the right with the lowest ionization energy and the easiest electron to remove. So let's talk about reading these photoelectron spectroscopy graphs. The y-axis is the number of electrons. It's a relative number of electrons, and you may see it labeled slightly differently, but you can always think about this as how many electrons are being emitted at that particular energy level. And on the x-axis, this is ionization energy. And again, you may see it labeled differently as change in potential energy or binding energy, but really this is ionization energy, and the y-axis is how many electrons have that ionization energy. Be careful about the fact that the x-axis is numbered backwards, and that's because it's easiest to think of the origin as being the nucleus and the farthest right regions of the x-axis being the valence electrons. And there may be breaks in that line because we maybe have many orders of magnitude different. Maybe this will be a logarithmic scale like there is here, right? Every distance is 10 times less. The height of these peaks tell us how many electrons there are at a specific energy. Lots of, and on the x-axis here, if we're far to the left, closer to the origin, that means a lot of energy is needed to remove those electrons. These would be the core electrons, which are hardest to remove. And peaks off to the right here are going to be your valence electrons. Very little energy is needed to remove those. And we want to know how much energy is required to move each electron. So there's some example graphs here. We might be able to identify what this element is because this one's been simplified and some of the noise and scatter has been taken out. You won't see graphs that look like this. This is what they look like in reality, but they are simplified in our class in order, and on the AP Chem curriculum in order to get the noise out. I look at this and I immediately read from left to right 1s2, 2s2, 2p6, 3s2, 3p1, and I recognize that's aluminum. 13 electrons in all. Which element is this? See if you can answer that one, and I'll pause the video here. Real spectra are not as clean as the ones you'll be given, just so you know, but we'll be looking at much more tidy pictures. So here's a couple of topic questions we can go on to next and practice photoelectron spectra interpretation. So as promised, there's the last few topics in spectroscopy that will be included in this video, starting with Beer-Lambert law, which is basically about spectrophotometry, and then finally those few other types of spectroscopy that we're required to at least be familiar with, even though the curriculum doesn't go into great depth on them, and that's infrared spectroscopy and microwave spectroscopy. So let's talk about Beer-Lambert law first. Think about light passing through a solution when you're thinking about Beer-Lambert law, or Beer's law for short. Spectrophotometry uses visible light, sometimes ultraviolet, to see how much light is transmitted. How much light is transmitted or gets through the sample can be related to how much light is absorbed with some simple math, but this math is really beyond the scope of the course. We're concerned with absorbance, how much light is absorbed. And Beer-Lambert law relates absorbance, big A here, to concentration of the solution, little c here. I'll think of concentration as molarity. How is it related? Well, it depends on how big this cuvette is. That's what the term B is, the path length. And for most purposes, the path length will be 1 centimeter because we're using cuvettes that are standardized in that way, effectively simplifying this equation to A equals AC. But this term A is the slope of the line on a Beer-Lambert law curve or graph, which relates the absorbance to the concentration. And that slope or that coefficient really depends on what substance we're talking about and what wavelength we've chosen. So in a lab that we do when we analyze percent copper and brass, we look at the relationship between copper ion concentration and the absorbance at 635 nanometers. That slope is this lowercase letter a, called the molar absorptivity coefficient for that substance at that wavelength. And a Beer-Lambert law graph is a powerful tool. In the textbook, they use a slightly different form of the equation, so don't be distracted by that. We want to recognize this on our purple reference sheets. This is another one of the equations that we're given, and it'll be one we want to refer to whenever we're dealing with spectrophotometry or Beer-Lambert law. When can we use Beer's law? Well, first of all, we need absorbance values to be less than 1. And that's because if a solution starts to get too dark, then it's so saturated that almost all light is being absorbed and it no longer has a linear relationship with concentration. So sometimes we might need to tweak the lab a little bit in order to make sure we're getting reasonable absorbance values. And this is something that we want to understand and know, that absorbance values greater than 1 will no longer give us a linear relationship with concentration. So we want to maybe dilute our samples to the point where the absorbance values are less than 1. Another thing that we want to understand about spectrophotometry is we have to pick the right wavelength. And we usually skip this part because we can cut to the chase in our lab work, but a real spectrophotometer will allow you to measure every wavelength. Our colorimeters only have 4 wavelengths, but ideally you'd measure absorbance at every single wavelength and then choose the best wavelength to use. And that's going to be wherever absorbance is the highest. So here in this particular example, it looks like about 510 nanometers is going to be perfect. Our absorbance values are right in the pocket here at about 0.5. And if the absorbance values were at 1.5, that's still the right wavelength to use. You just want to dilute your sample until you get absorbance values less than 1. But wherever the absorbance is the highest, that's the wavelength you want to use to analyze your sample. So here we'd refer to that as lambda max. Once we've chosen the right wavelength, then we have the next job is to see what that relationship between concentration and absorbance is. And if we have a graph like that Beer-Lambert law or a calibration curve, so to speak, then we could use this to determine the concentration of unknown solution. So let's say our unknown solution has an absorbance value of 0.275. That looks like it corresponds to a concentration of 0.05 or maybe just below that. So we do this in a lot of labs in ChemMR, and we do a couple of times in AP Chem as well. So we want to make sure we understand how Beer-Lambert law is applied here. And not only do we want to understand the standard curve here, the calibration curve, but we also want to understand how we pick the best wavelength to get or to use. So there's a couple of good topic questions that review this, which are important for us to consider. Pause the video here, take a look at those topic questions, and then we'll finish up our discussion of spectroscopy. So our last topic is going to be infrared and microwave spectroscopy, and there's really only a few comments to make here, a few things we need to remember here. Remember that spectroscopy in general is just the study of how light and matter interact. And we've talked now about spectrophotometry, that's Beer's law, also known as colorimetry. And we've talked about photoelectron spectroscopy and how to interpret those PES graphs. There are two other types of spectroscopy. Those are infrared and microwave spectroscopy. And these are powerful tools, although they aren't studied in great detail in the AP curriculum. All we need to know is that microwave radiation causes molecules to rotate, and infrared radiation causes molecules to vibrate. Certain molecules will rotate when exposed to microwave radiation, and certain molecules will vibrate when exposed to infrared radiation. Think about the fact that a microwave oven usually has a turntable in it. So when you microwave a molecule, it will rotate just like the turntable of a microwave oven. And infrared will cause molecules to vibrate. So these are just sort of an afterthought, and that's really the scope of the learning objective in AP Chem about these other types of spectroscopy. They're really interesting bits of technology, but we don't need to go into great detail understanding them. To give you an idea of the types of questions you might be asked about infrared and microwave spectroscopy, I'll refer you to these two examples. The last thought that I wanted to mention, sometimes students ask whether mass spectrometry is a type of spectroscopy. And remember, mass spectrometry is really how we determine the average atomic masses for elements. And we refer to mass spectra, but it's really not about how light and matter interact. So that's a separate topic altogether. It might be helpful to note that visible light is what's associated with, spectrophotometry, and really what's happening when we apply visible light to samples is we're causing the electrons to transition between different energy levels. So that is what spectrophotometry or visible spectrophotometry is all about. And as we go up from microwaves to infrared to visible light, of course, we're talking about higher and higher energy of light. And finally, we get into UV and X-ray. Now, UV light is sometimes used in spectrophotometry, but as we get to higher energy UV light and X-ray light or X-ray radiation, we're talking about photoelectron spectroscopy. So it maybe makes sense that visible light, kind of lower energy light, is going to get the electrons to jump around in an atom, but UV and X-ray light is going to cause them to jump out. And when they start jumping out, that's the photoelectric effect. That's ionization energy. So it should make sense that even higher amounts of energy or even higher energies of light are going to cause electrons to actually be ejected as opposed to just jumping around. So as we go from low energy to high energy light, we get very different phenomenon in matter. Molecules rotating, molecules vibrating, electrons jumping around to different energy levels, and then finally, electrons being ejected from atoms altogether. So that wraps up all of the topics in this unit. Hopefully that was helpful.